Okay, hello everyone. So let's now have, or we will now discuss. We are done with chapter three. Uh, it's all about particle physics. So now let's go to chapter four, to our next chapter, and the chapter four. It's all about the quantum theory of light. Okay, so let's talk about the quantum theory of light. Okay, so humana ta sa relativity, no? Take note, modern physics is ito nga siya gaduha. No? So, natay first nga part is for relativity, okay, by Einstein. Ang second nga part is and quantum mechanics by Max Planck. Okay, so we are now in the part 2 sa ato ang modern physics, the quantum theory of light. Okay, so we have to take note. I think this will be your last physics, no? Modern physics kaya ang last niyo physics. So, humanata sa mechanics, humanata sa thermodynamics. We are also done with electromagnetism. So, the last part is this modern physics. So, we know, if we recall, um, sa atong mechanics is all about Newton, no? Isaac Newton. Okay? So, kung yung hisgot ko mechanics, ang pinakasikat na tao sa mechanics is we have this Isaac Newton. For electromagnetism, kung hisgot ko electromagnetism, then ang una na to dumduman nga person ani is si Maxwell. Okay, because he actually completed the theory, the concept of electromagnetism by just deriving the four Maxwell's equation. So if we recall, there is this four Maxwell's equation, and kaning upat ka equation mo yung nagkumpleto sa concept of electromagnetism. So from these four Maxwell's equation, ma-explain na ko tanan unsa ang naa sa electromagnetism, tama ba? Unsa itong four Maxwell's equation na ako'y Gauss law. Okay, Gauss law. I also have Faraday's law, and na ako'y Ampere's law. Okay? These are all equations, right? These are all equations. Gauss law is in terms of integral nga equation. We can write this as this one, no? The flux equal to Q over epsilon naught. Faraday's law, it simply means that E dot dl, there will be a an induced EMF, okay? An induced EMF, E dot dl is equal to the minus change in flux over change in time. This is the Faraday's law. And the Ampere's law, it is just equal to integral of the magnetic field dl equal to mu naught I plus some correction um, epsilon naught mu naught d flux over the dt. Okay? So, pa isa, no? We have, there's no name, no? Wala si pangalan nga law. But it simply means that the the B dot dA, the flux for a closed surface is equal to zero. Okay, so these are the four Maxwell's equation that completes the concept of electromagnetism. So mechanics is nakoy Isaac Newton, electromagnetism nakoy Maxwell, thermodynamics and statistical mechanics, no. Thermodynamics, kung hisgot kog thermodynamics, ang madumduman ako nga pangalan is daghan, no, nakoy Lord Kelvin, nakoy Carnot, okay? Si Carnot, si Kelvin, ah, si Helmholtz, and so on. Okay? Helmholtz and so on. So these are branch of physics na with corresponding person kung kinsa ang pinakasikat ato nga physics. Okay? So we have this mechanics, electromagnetism, thermodynamics, and also relativity. So kung may relativity, it's all about Albert Einstein and so on. So next to relativities, we have this quantum physics, or we call this one as quantum mechanics. Okay, quantum physics. So next to relativities, we have this quantum physics or quantum mechanics. No? Quantum mechanics. Okay, so it is also a branch of physics, and it started. So asa nag-start ang quantum physics? It started uh, with a problem of with a problem of classical classical statistical mechanics. Okay, so naay problem sa thermodynamics or statistical mechanics na maglisod sila solve. Okay, maglisod sila solve. That's why naay another field of physics, which is we call this one as quantum physics or quantum mechanics. Okay, so sa una sa thermodynamics, katong wala pa yung quantum physics, naglisod sila og solve aning they tried calculating the intensity of radiation. The intensity of radiation. So this is in thermodynamics ng problem, no? So muna ang problem sa una before nag quantum physics. Uh, they tried calculating the intensity of radiation at a given wavelength. Okay, at a given wavelength. Okay, so unsa ano pag-solve, unsa kadako o unsa pila ang intensity sa radiation at any given wavelength from a heated cavity, a heated cavity. So again, this is a problem nga naa sa thermodynamics. No? When you heat a material, what will be the intensity of radiation nga naa ato nga material, no? So maglisod silang sulbani sa una, no? Before ang quantum physics, maglisod sila og sulbani. So the desperate solution to this radiation problem was found by dinanay sulod si Max Planck in 1900s. Okay. So si Max Planck mo'y nag-solve ani nga problem sa una. Okay. And by the way, Max Planck is actually the father of quantum mechanics, no? Siya gid ang nag-start. Siya gid ang father of quantum mechanics. Okay? Kung si Einstein ang father of relativity, then si Max Planck mo'y siya gid nag-start aning quantum mechanics or quantum physics, no? So nag-start siya sa problem nga we call this one as black body radiation. Nag-start gid siya dira, no? Kung saan ako pag-solve ang intensity at a given wavelength from a heated cavity. When you change the temperature, what will be the intensity of the radiation? Okay, of the radiation. So Max Planck in 1900s answered this or solve this problem, no? Solve this problem. So let's start um, with this concept of black body radiation. So this is a problem of a black body radiation. So what will be unsa ang na-formulate or unsa nga equation ang na-formulate ni Max Planck para ma-answeran nato ning problem. Okay? So Max Planck arrived at the correct spectral distribution of cavity radiation by allowing only certain energies for the radiation emitting oscillators in the cavity walls. Okay, so basta no, na-answeran niya ang problem. He derived equation of distribution, no? Spectral distribution for cavity radiation by allowing only certain energies from the radiation emitting oscillator. So let's later lantaw na to unsa ning equation ang iyahang na-derive. Okay? So in this topic, in this quantum physics nga chapter, we will actually discuss five topics. Okay? As I said, ang pinakauna na to ang discuss is we have this black body radiation. Okay, diri man nagsugod, no? Diri man na buhat or nahimo ang quantum mechanics from the black body radiation problem. Okay? Black body radiation problem. So we will discuss black body radiation. We will also discuss photoelectric effect. Okay? Photoelectric effect. Um, We have also Compton effect, Compton scattering. Okay, so ilang taon na to na later. So for black body, makuha na ko ang distribution sa iyang intensity, no? Spectral distribution. Photoelectric effect, kuha na ko ang pila ang working potential, pila ang kinetic energy sa electrons or photons, pila ang energy sa photons nga kinahanglan para ma-knock out niya ang mga electrons. So I will discuss that later. Compton scattering, one of the attenuation mechanism is this Compton scattering. So naikalayan aning duha, no? Unsay kalayaan sa photoelectric effect ug Compton effect. I will discuss that one later. And then we have Rayleigh-Jean law and the particle wave duality. So we have Rayleigh Jean law, and then the last one is we have a particle wave duality. Okay, so I think nanata idea gamay sa particle wave duality, no? So ang light is a particle and a wave, no? So natin kitawag ng particle wave duality. So let's start with black body radiation. Black body radiation. Okay. So black body radiation, we will now predict, okay, predict the intensity, radiation intensity, okay, at a given wavelength, at a given wavelength. So what will be the radiation intensity at a given wavelength emitted a hot by a hot glowing solid at a specific temperature. Okay, at a specific temperature. I think nano tay idea gamay ani, no, kaning black body kaning bitong painit kag uling, why is it nga ang color niya when you increase the energy. Okay, kung dako kay heat, kung increase akong heat or increase akong temperature, no, what will happen to the color of that uling is mo change into red. Okay, so that somewhat is an example of black body radiation, no? So nagtaon na to ha, black body radiation. Tinawag niya black body radiation image. May image. Ah, ingani sa color, no? Kaya nganong mo glow siya o nganong mo red yung color, no? And ang question is kani, no? When you increase the temperature, say for example, sa anong red yung color and so on. So question is, how will you calculate the intensity of that radiation? So we will answer that one later. Okay. So when you increasing the temperature, kung dako kay temperature niya, what will happen mo? We can calculate the intensity of the radiation at that specific temperature. Okay. So that sa una in 1972, ano, this is not 1972, but we have this person named um, Wedgwood. Thomas Wedgwood. Okay. Paano siya, no? Kaning relative ni siya ni Charles Darwin. Charles Darwin. Okay, and then kuan po siya. Renowned maker of China. Okay, renowned maker of China. Okay. Si Thomas Wedgwood. Ingon niya, no? Ingon niya, he observed that that all the object in his oven, okay, in his oven, regardless of shape, regardless of shape, size, regardless of shapes, yang size, chemical properties, okay, and chemical properties, and chemical properties or chemical nature, okay, became red. Of course, ma-observe mo na ito ni karon, no? If you increase the temperature, uh, butang ka any object sa imong oven or what, the color will change to red at the same temperature. Okay? So, mura niya na-observe, pero wala niya na um, quantify unsa kadako ang intensity ani nga radiation. Okay? So, mura to yung observe, no? Observe niya nga mo red yung color. Why is it nga mo red siya? It's because of this black body. Okay? And black body is defined as, okay, as defined as an object, okay, as an object that absorbs. So this is by definition of black body. Absorbs, sorry. Absorbs all electromagnetic radiation, okay, EM waves or EM radiation, sorry. It absorbs. Black body is an object that absorbs all electromagnetic radiation falling on it, okay? Falling on it and consequently appears black. Okay? So, black body is called perfectly absorber. Okay? I-absorb niya tanang energy, tanang radiation from the electromagnetic radiation. So, we call this one as perfect absorber. Okay? In 1859, we have this person named Gustav Kirchhoff. I think na nadungganan niyo siya sa electromag, no? Kani bitang una kay circuit, um, yeah, electric circuit. You can solve the currents using Kirchhoff's rule, no? Kirchhoff's rule katong ingani, no? Ito na yung mga resistor, tapos na ingani. So siya tong tao, no? Siya tong tao. Kana tapos you can calculate the current uh, of this electric circuit. You can calculate the current using the Kirchhoff's rule. So muna siya, no? In 1859, si Gustav Kirchhoff derive the power per unit area. Okay, so na-derive ni Gustav Kirchhoff this equation, EF equals some function J, which is a function of frequency and temperature, times the AF. So what is this EF? This one is the, yani, this one is the power per unit area. Okay, per unit area per unit frequency. Per unit frequency. So, unsa ni siya? More siya intensity gihapon, no? Power per unit area. Take note, power per unit area is actually equal to intensity, no? Intensity is defined as power per unit area. But in this case, the EF is na po koy more siya intensity per unit frequency, no? Power per unit area, that's frequency, tapos no, power per unit area is intensity, per unit frequency, that is my EF. Okay, that's my EF. And this J, this one, okay, this one is some function. We call this one as universal function. So depende sa imong material nga gigamit sa system nimo or what. So this is just a function. We call this one as universal function, which is a function of frequency and temperature. So kana, no, we don't know that sa kani nga panahon wala pa sa kabalo unsa ning exact na function J. Okay, J. So we just call that one as universal function, and this AF is called the absorption power. So depende, si AF is called the absorption power. So depende no sa imong material, no, sa imong black body material, kung unsa siya ka kanang unsa siya kadako ang iyang ma-observe nga energy. Okay, depende sa iyang material, no? So we call that one as absorption power. So uh, so kinsa kay nag-derive ani si Kirchhoff, no? Si Kirchhoff derive the intensity per unit frequency, and it is just equal to that times absorption power times the universal function. Now, after 20 years, okay, after 20 years in 18 in 1879, after 20 years, niabot ni nga tao, no, si Joseph Estefan, okay, and he actually derived the so-called Estefan's law. If balik ka sa ato ang thermodynamics, I don't know if gi-discuss ni sa thermodynamics, no, the Estefan's law. The Estefan's law states that the intensity per unit frequency, we call this one as E total, is just equal to some constant sigma times T to the power of 4. Okay? Times T to the power of 4. So, this sigma, okay, so si Stefan, we call this one as Stefan's law. I think napag-ining, kung if ma-remember ninyo, natay Stefan's Boltzmann's law. Okay? Somewhat, ingani ra sa form, no? The radiation is equal to, the intensity is equal to the fourth power of the temperature. Okay? So, as you can see here, your J universal function is somewhat na specifies into this, no? Na specifies into this. It says that the intensity, um, the power per unit area per unit frequency is proportional to the T to the power of 4. Okay, where sigma, okay, si sigma is some constant. Okay, and this constant is equal to 5.67 times 10 to the minus 8 watt per meter square times K uh, per meter square K to the power of 4. Okay, K to the power of 4. Sakto ba na? Yeah. Take note what watts per meter square is a unit of intensity. Okay, and then when you multiply it by temperature here must be in Kelvin. Okay, the temperature here must be in um Kelvin. Okay, so as you can see, your sigma is some constant 5.68 times 10 to the minus 8 watt per meter square K to the 4 Kelvin to the 4. So therefore, this E here, the E total is actually your intensity per unit frequency or just intensity. Okay, so this sigma, I think if ma-remember niyo sa thermodynamics, we call this one as Stefan Boltzmann constant. Stefan Boltzmann constants. Okay? If na-remember ninyo, muna itong gigamit, say for example, how will you measure the temperature of the sun? Okay? Uh, how will you calculate the temperature at the surface of the sun? We will use this equation, this Stefan's law, to calculate that one. Okay? I think maghatag ko example ani later. Okay? The general law is, we have the Stefan's law, assuming that your black body power absorption is equal to 1. Okay, if you generalize the Stefan's law, you can um, have this equation. In general, we have the E total is equal to A sigma T to the 4. So mo gini ang general niya expression. In case for black body, okay, so this is the general law, yeah. For black body, your A is equal to 1. Okay? So that's why nananong ko sigma T to the 4. Okay? Because your A here for black body is equal to 1. Okay? So this is the general expression of my intensity. And take note, your intensity is proportional to the power to the temperature to the power of 4. Okay? Temperature to the power of 4. For example, So let's have an example. Kato ko yung no, calculate the surface of the temperature at the surface of the sun. Ito. Example. So for example, oy, wala ano to. Example 1. Okay, this one. Estimate the surface temperature of the sun. Okay? So unsa ka init pila ang temperature at the surface of the sun using this Stefan's law. Okay, Stefan's law ang gamiton lasa. So Stefan's law applied to the sun. Estimate the surface temperature of the sun from the following information. We know the sun's radius. It's given by this. Given ang sun's radius Rs equal to 7 times 10 to the 8 meters. Given also ang distance between the Earth and the Sun, which is equal to 1.5 times 10 to the 11 meters. Okay? And the power per unit area at all frequency from the Sun is measured to be 1,400 watts per meter square. Take note, watts per meter square is a unit of intensity. And we assume that the Sun is a black body. It means that in general, Stefan's law, your A in that equation is equal to 1. We assume that the sun is a perfect absorber or it is a black body. Okay. So given no na ako sun's radius, kay kuhaan mo na to ang temperature sa surface no. So dapat given imo ako ang sun's radius kay para when this is your sun, yellow ang sun. Yellow. Yellow dire. Wala yellow. So kung mo na ang sun no, the radius is Rs. Okay? And then we will estimate the temperature, pila ang temperature at the surface of this sun. Okay? So we know A is equal to 1 and the intensity. Take note, given po ang power per unit area. Take note, the intensity from the sun is measured at the earth to be equal to 1,400 watts per meter square. Okay? So given is that we have this Stefan's law. The E total, okay, E total at the surface, meaning at the radius Rs, okay, the intensity at the surface of the sun is equal to sigma T to the 4. Okay, so this is my Stefan's law where A is equal to 1. Okay, so this will be the intensity or the total power per unit area at the surface of the sun, which is equal to, I think this is given, no, this is not given. So, dili given ang intensity at the surface, no? Dili siya given. So, ato ang kuhaon, once makuha nato ang intensity at the surface of the sun, makuha nato ang temperature dayon, no? Tama ba? Again, if I can solve for the intensity at the surface of the sun, then I can get the temperature. I can approximate or I can estimate the temperature at the surface of the sun. So how are we going to solve first the intensity at the surface? We have this so-called um, conservation of energy. Okay, we have this so-called conservation of energy. Okay, to solve for the E total Rs, we have this conservation from conservation of energy. Conservation of energy. Okay, we have this E total at the surface of the earth, at the surface of the sun, Rs, okay, times the surface area. Unsa ni siya? This is actually the power, tama? If take note, the intensity intensity E is equal to power per unit area. So therefore, if you solve for the power, solve for the power that's equal to intensity times the area. Okay, so in this case, na ko'y intensity at the surface of the sun, Rs, okay, times the area, surface area of the sun with radius Rs. Take note, this A here is not just an area uh, of a circle or what, but it is a surface area of the sun. Okay, surface area of the sun. Okay, so it means that if your energy is conserved, then therefore the power is also constant. It's also conserved, no? Power is also conserved. It means that the power nga naa sa sun must be equal to the power nga imo ma-observe sa Earth. And it is equal to this intensity at the R, okay? Or at the surface of the Earth, which is given, I think it is given, na no, kanin, the intensity at all frequencies from the sun is measured at the Earth equal to 1,400 watts per meter square. So muna ato ang nakuha nga intensity because diri man ta na-observe, no? Na-observe na to at the surface of the Earth, nakakuha ako og intensity from the sun which is equal to 1,400. So this one is given. Okay, this one is given 1,400 watts per meter square times the surface area of the Earth, which is equal to 4 pi r squared. Okay, so R is your no, sorry. R here is not the radius of the Earth, but R is the distance between Sun and Earth. Okay, which is given also, no? Nakoy R is equal to 1.5 times 10 to the 11. Okay, so the intensity at Earth, where Earth is, it has a distance equal to R from the Sun. Okay? Okay, kung muna ang Sun, muna akong Sun, no? And then muna ang Earth, muna akong Earth. So, ang power nga gi-emit ani nga Sun, it has a distance of R, no? It has a distance of R. It has a distance of R. And from conservation of energy, dapat ang power dari must be equal to the power here. Okay? Ang intensity magkahinay. Okay? Magkahinay ang intensity kung magkalayo siya sa magkadako imong R, magkalayo siya sa source, ang source na to is ang sun, magkalayo siya sa sun, magkahinay ang intensity but the power is constant. Okay? So that's why kani the power at RS is just equal to the power at R. So muna akong RS, no. Muna akong RS, kani akong RS ang surface sa sun. The power at point RS, okay, RS from the center of the sun is just equal to the power at point P, at at point P where your Earth is located, and that has a distance of R away from the sun. Okay? Again, power kay dapat equal lang, okay? Power kay dapat equal lang kung ako'y source. Ang power kay equal lang sa bisag asa nga point. Okay, in radial direction, no, bisag asa nga point, power is just the same, but ang iyang intensity kay mag-change, no? Magkalayo ka sa, of course, no, magkalayo ka sa source, magkagamay ang iyang intensity. Kay layo man ka, no? Gamay ra yung madunggan or kung sound na siya for example, then ang intensity kay magkahinay kung magkalayo ka sa source. But take note, the power is just the same. From conservation of energy, power is just the same. So, using that, we have this, okay? We have this equation, and I think Rs is given. R is also given. Take note, I'm sorry, R is not the radius of the Earth, but the distance between Sun and Earth, okay? Ang kalayo ni Earth gikan sa Sun, okay? And that is given in the problem. RS is also given. So, given po ang i-total R, the intensity at Earth, ngayon ang atong measure, given si R, we can solve for the intensity RS. And again, once I solve for the intensity RS, I can solve for the temperature, which is muna atong gipangita, no? Find the surface temperature of the sun. Okay? So using this, we have, okay, so nako ingani, no? I-rewrite lang nako, no? The intensity total RS, which is unknown, times 4 pi RS square. Take note, surface area is 4 pi r square. Okay? And then this is E total at point R times 4 pi r square. You can cancel out the 4 pi. Cancel out na tong 4 pi. So as you can see here, the intensity at the surface of the sun is equal to E total intensity nga na-observe na to sa Earth times R square over RS square. Okay? So this is, when you solve this, we have This is 1,400 watts per meter square times ang distance nga r square, r, that is equal to 1.5 times 10 to the 11 meters quantity square over rs. Ang rs is the radius of the sun, equal to 7.0 times 10 to the 8 meters quantity square. Okay, and then okay, calculator. Okay, anyways, so this is my E total, the intensity at the surface of the sun. We can solve using Stefan's law. Using this, E total at Rs is equal to sigma T to the 4. Okay, we can solve now the temperature, equal to um, E total at Rs, tama, over sigma raised to the power of 1/4. Okay? And we know E total is equal to this. So ako lang kopya ko na lang po. 1,400 times 1.5 times 10 to the 11 meter square over napakoy 7 times 10 to the 8 meter square, but I have a sigma which is constant, and sa itong sigma gani, sigma is equal to 5.67 times 10 to the minus 8. Okay? So na ako 5.67 times 10 to the power of minus 8. Okay, minus 8. 5.67 to the power of minus 8 raised to the power of 1/4. And if you use calculator, the temperature at the surface of the sun is actually equal to 5,800 Kelvin. Okay? So, ma-estimate nimo using Stefan's law lang, no? Using Stefan's law, ma-estimate na to actually ang surface temperature of the sun. So, nga na siya kainit din, no? Nga ni kainit ang surface sa sun. 5,800 Kelvin. So, kung mato sa sun, wala pa ta niabot, wala na nahilis na ta or nalanay na ang kwan. Nalanay na to ang gisakyan nga spaceship or what, ano? So, kung gusto ka moadto, so ay mong buhaton kay mag-build ka og material, nga dili siya madaot o di siya malanay at temperature equal to 5,800 Kelvin, no? Dapat ang melting point niya is greater than this temperature, greater than 5,800 Kelvin. And I don't know if naabay material nga ang iyang melting point is greater than this. Nantaw na to ha, mangita ta og material melting point greater than 5,000 Kelvin. Kaya kung nagali, posible nga makaadto sa kuha, no? Posible nga makaadto ta sa surface sa sun, no? As you can see here, which material has highest melting point? Natay gitawag nga tantalum carbide and hafnium carbide. And then ang ilahang melting temperature is greater than 4,000 Kelvin. Okay? 4,000 Kelvin. So wala ra gyapon siya nabot og 5.8. So malanay ra gyapon siya, no? Malanay ra gyapon ning ato ang greater than 4,000. So pero dapat 5,000 dapat na, no? Dapat 5,000. What is the highest melting point? 3,000. Okay, so kana, no? So kung nagtaon nimo, imposible gyud nga makatuta sa sun because tanaw ni mong temperature, ma-estimate mong temperature sa surface, and it is greater than the melting point of all the materials nga nga present sa earth, no? Gawas na siguro kung na meteors nga moabot or mahulog diri tapos katong nga material kay grabe ka dako ang melting point. So, posible ta makabuhat og kanang spaceship nga ana. Okay. So, kana no, wala pa ka naabot sa sun, wala nahilis na imo kuan. Lanay na imong spaceship or what. Okay? Because of this grabe kadako nga temperature. So, ma-estimate na to again. We can estimate the surface temperature of the sun using just this Stefan's law. And what is that Stefan's law? Stefan's law is just equal to the intensity is equal to the sigma t raised to the power of 4. Okay, raised to the power of 4. Now, okay, so we have that. We have that 5, 8. Okay. Okay. So next is we have this J, right? As you recall, J is equal to J as a function of frequency and temperature. We call this one as universal constant. And there is this set nila ng universal not constant but universal function J as a function of frequency and temperature. They set this one as U F T UFT, another function na po no. Ang function na another function U as a function of frequency and temperature C over 4. Okay, C over 4. From this, they set U ft equal to this function. Okay, anyways, don't mind this function. It's just a function of frequency and temperature, no? Frequency and temperature na ko minus bf over t. Aha, this b here is a Boltzmann constant. Okay, Boltzmann constant. A is some function, a constant function A. F is frequency and T is your temperature. So we have this function, an exponential function. Okay, exponentially decreasing function e to the minus bf over t. The universal function is pangitaan nila og equation which is equal to this f to the 3 and then e to the minus bf over t, where this kanisya is actually, we call this one as the Wien's exponential law. Okay, Wien's may pagbasa ni or Wien's, pwede ra Wien's, no? Or usay kay Wien's ilang pagbasa. Exponential law, exponential law, and it is based from the Maxwell's velocity distribution. Okay, so no need to derive this one. Okay, so we assume that we know this one. We assume that kabalo na tani what di na to i-derive na, no? Okay, but ang derivation niya is gikan siya sa kaning kang Maxwell's velocity distribution. I think if mobalik ta sa thermodynamics na ni siya, no? Kani bitang Maxwell's velocity distribution function. So base siya ani, okay? And we call this one as Wien's exponential law. So it is a if you graph this one, okay? If you graph this one, ang iyahang porma is ingani, no? If you graph this function, ang porma niya is actually this one. Okay. This is the Wien's law. Okay. So if you graph that, you will get this figure here. Okay. But na problem. Okay, na problem gamay. Kung lang taon nimo, ibalik ka diri, no? Ang problema ni is this. This is the kaning blue. Kaning blue is muna ako ang Wien's exponential law or Wien's exponential law. I don't know saan pag-pronounce. Wien's or Wien's. Basta muna siya, no? That's the exponential law. Kaning blue nga part, okay? Muna ang exponential law if you graph that function. The energy per unit volume per unit frequency of radiation. Okay, kanang U. Okay, the energy density. We call this an energy density because we call this one as energy density or energy per unit volume. Okay, kaning U, no? Kaning U is called the energy density. Okay, or energy density or energy per unit volume. Okay, so basta may kung density ka kay per unit volume, per unit area, per unit length pa siya, no? So that's an energy density. If you graph that, nakoy makuha ang ingan niya graph. Okay, kaning blue nga part. Okay? It is an exponentially pa-increase siya and then pa-decrease din sa layo. Okay? And take note lambda. Take note lambda is dependent siya sa frequency, no? Tama ba? Because as you can see, nakoy V is equal to lambda F. So if I have F, kung tawagin mo F cube, that's F cube, then that is actually equal to 1 over gamma cube. Sakto ba? 1 over the wavelength. Sakto because F is inversely proportional to your lambda. So if I have F cube, then somewhat it is proportional to 1 over lambda cube. Okay? So as you can see, if you graph the energy density, the U, as a function of lambda, okay? As a function of lambda, ang makuha ni mga function is this one. Okay? But ang problema ni is this. Kung nagtaon ni mo experimental points, may problema when when your lambda is just 1 mu m, 1 micrometer, 2 micrometer up to mga diri dapit, no? Kung nagtaon ni mo ani nga region. Kung nagtaon ni mo ana nga region. Kani nga region dapit diri. Okay? Walay problema. Mo agree ang imuhang experimental points sa ato ang Wien's exponential law. Tama ba? But when you increase the lambda, when you increase the wavelength, ang nahitabo kay kung taon nimo increase nimo up to 18, no? Kay nag-experiment ani. Experiment ani, no? When you increase the wavelength, what will happen is nagkalayo siya sa imuhang Wien's exponential law ni mga equation. Aha. So for shorter wavelength, gamay lang wavelength, it agrees with the law is it agrees with this exponential law. But when you increase the wavelength, okay, ako din mo ang wavelength, mugamay ang frequency, tama ba? Nakuha ng wavelength, mugamay ang frequency. Your experimental points kay dili na siya, wa siya nag-agree sa imong exponential law. Okay. Dili na rin isulod si Max Planck. So, nana din si Max Planck. So, in order to answer this one, why is it that dili mo agree ang akong experimental points sa imong exponential law? Okay? Then there must be something wrong with this region, kaning region sa imong wavelength dari, no? I don't know if wrong ba siya, but naigamay nga missing, no? Naigamay nga missing. So, ang missing, kay dito na dayon nisulod si Max Planck. So, siya ay nag-answer aning nga problem, no? Siya nag-answer ng aning nga problem. So, to solve this one, to solve this problem for for longer wavelengths, okay, para ma-equal ang imong experimental points or mo-agree mo experimental points sa kaning imong law, equation law, naa si gisolve actually ni Planck, okay, gisolve niya ang energy density, and the energy density nga yang na-solve, again, we will not derive this one, okay, at di na to i-derive, no, kaya di po kabalo mo derive ani, anyways, okay, so ang Wien's law is gi-rewrite lang niya gamay, okay, na siya gi-rewrite gamay, and Max Planck derived the energy density U equal to this, grabe kay specific nga function, okay? HF cube over C cube 1 over E to the HF over ito na ako, salat ko sige. E to the HF KBT minus 1 kana. Okay, kadto lang mag-charge ako. Okay. Aha. So, ito, katong imuhang lantaw na ko ang katong Wien's exponential law. Same lang, tama ba? Nakoy F cube. Pero wala niya gi-specify ang constant. Pag abot ni Max Planck, gi-specify niya ang constant nga A equal to 8 pi h over c cube. Okay? So now, lantaw na ko isa-isa ko na to ng mga constant, no? Isa-isa ko na to ng mga constant. So sa iyang pag-solve sa black body problem, na formulate niya ang quantum mechanics. So asa dapit ang quantum mechanics ani nga part, okay? Sa kadit lang. Okay. Okay. So hadapit ang quantum mechanics ani nga part. Tawo na to, no? Uh, the U is equal to AF cube tapos times exponential decay nga e to the minus bf over t. And in iya is na koy 1 over e to the hf over kbt minus 1. Okay? So, nagyapon siya constant. Ang iyang beta diri is some constant h over kb because this is a frequency over temperature. So, nas ang gi-specify gihapon niya ang constant equal to h over kb and then nakoy minus 1. If you graph this one, then it will agree ang kaning equation. Okay, kaning equation kay mo agree sa kaning iyahang experimental points at any given wavelength. Okay? At any given wavelength mo agree ang akong kaning Planck's equation, kaning U nga giderive ni Planck's sa kaning ato ang experimental points. Bahalag taas pa na nga wavelength, bahalag mubo pa na nga wavelength, mo agree ang akong experimental points sa kaning mo agree akong kaning function ako sa energy density sa kaning akong experimental points. So ingani kagaya si Planck, kagaya kasi Planck, may kasi Planck, ka-level na sila or mag-solve na sila ni Einstein sa una, no? Kauban na sila ni Einstein sa una. So ingnon ra ni Einstein si Planck ang solve ni kani din masolve niya gyud. Aha. Dili na, no? Dili ni sulod si Max Planck and asa dapit karon ang quantum mechanics nga part. Ang quantum mechanics nga part is this constant h. Okay. This h here is called the Max Planck constant. H is called the Max Planck constant. Okay? So grabe si Max Planck no ihaging gamit iyang pangalan no sa kaning constant. Then diri ni sulod si quantum mechanics. Muni ang kalay-an sa classical ug sa quantum mechanics. Quantum mechanics is na ako'y constant nga gitawag nga Max Planck's constant. Okay? Kung makita kay kag Max Planck's constant sa equation, then kana siya nga field is in quantum mechanics na field. Okay? So muni ang isa sa nag-distinguish isa sa kalahian sa classical ug sa quantum mechanics sa part. Of course, kay si Max Planck man nag-solve so iya gibutan yung pangalan, no? Kung makakita kag H or H bar, okay? Kung makita kag H or H bar, then this is a formulation in quantum mechanics. Okay? Wala man ni sa classical. Kaning Max Planck's constant wala ni siya sa classical mechanics nga field. Naara siya sa quantum mechanics nga field. Okay? So this H is a Planck's constant which is equal to again ang nag distinguish sa classical ug quantum mechanics nga field is kaning gitawag na ko nga H or H bar and we call this one as Planck's constant. Okay? So grabe si Max Planck no iyarang gisolve unsa ra iyang gisolve gani? Ang iyarang gisolve is only the black body radiation problem nga dili nila masolve sa una before ang quantum mechanics. And gikan ato nga problem naka-derive siya or nakakuha siya ning Planck's constant and from this dito na dahil nagsugod ang quantum mechanics. Okay? Na ko yung mga Schrödinger equation nga nagyapon siya yung Max Planck naging siya Max Planck's constant permanente, ha? Or H bar or H. Okay? So ining H gani it's just a constant. Okay? It's just a constant. H is equal to 6.626 times 10 to the minus 34 joule times second. We also have this H bar which is equal to H over 2 pi lang. Take note of this because sa atong Schrödinger equation, dili lang H ang perminti mo appear kundi H over 2 pi. Okay? Sa tanang nga equation nga na-derive nila later, na-derive nila kasagara is dili lang H but H over 2 pi. So that's why natay gitawag nga H bar and they let that one as the H bar they let H bar as equal to H over 2 pi. Okay, but originally, ang na-derive ni Max Planck is kaning H equal to 6.626 times 10 to the minus 34 joule times seconds. This KB, kaning KB is the Boltzmann constant. Okay, Boltzmann constant equal to 1.38 times 10 to the minus 23 joule per Kelvin. So, unsa gani siyang KB gani sa atong thermodynamics, no? We call this one as Boltzmann's constants. Okay? Boltzmann constants. So, din na yon. After this, quantum mechanics na dahil nga part. Okay? So, kana lang, no? Ang pinaka nga concept is si Max Planck gi-solve niya ang black body problem, and then from that na derive niya ning energy density way in which natay na derive nga constant, and that constant is this Max Planck constant H. Okay? Aha. So diri nag-start din ang quantum mechanics. Okay, I think that's it. So tomorrow I will discuss the quantum of energy. So kaning packets, energy packets. So i-discuss na ko ni siya tomorrow sa ato sa atong klase. Okay? That's it for this video. So see you tomorrow. Bye-bye.